concept is when you take into account both, you try to have the intersection. You try to still be on the right side of that boundary. So what you learn from looking at it in that broad sense is anything can fail. There's never going to be a probability of zero. And it becomes very dependent on the industry and the application, how small or big that unknown, that area of overlap where you will have a failure can be. And there's an interesting equation that came out of that book about acceptable failure probability. And as you can see, it depends, what are we looking at? Is it a whole dam for everyone? Is it something that is going to be used by, what are the consequences of a failure? So they call it the social criterion factor. And it becomes a higher value. See, you go from 0.005 to 5 if it's an offshore structure. So when we're thinking about incidents that can happen on a drilling rig, it's because overall, when everything is, if you take the worst case scenario, they are further into the risk of a failure than a bridge where, you know, a tunnel here in Boston where 50,000 people go through every day. It's just the way it is. It's kind of a cynical way. It's kind of saying, well, it depends how many people are involved, if we're going to care very much or how much we're going to care. It's the same between aviation, the very small aircrafts, and the big jets. A small aircraft has more flexibility, the inspection, just the technology is not exactly as reliable. So if we go back to this plot here, the circle is bigger, and therefore you're increasing the overall probability per person of having an incident. Related to this concept of a probability of failure, what we have here is how much the stochastic factor, safety factor. This is essentially becoming a little bit more of an actual safety factor as opposed to the calculated value. So what happens is if you say, well, what's the probability that 10% of wheels on car fall off? It's very low, and your factor of safety for that to happen is more than 2.5. But if you say 1 in a million, then it depends how everything was calculated in the first place. If on the first place you calculated it as a factor of safety of 3, you end up with 2. If you calculated 1.2, now you're below 1. So yeah, it will fail. So it really depends on this probability factor. So it's an additional variable when you want to know your actual factor of safety is how much of a life are you looking at, and how many things you don't know about. When you go to the lower probability, the Six Sigma type concept, there's a lot that you just don't know. It's very hard to get there. You need to really have a control environment, which is hard when you go build a structure and somebody else uses it and maintain it. You know, maybe they won't put all the screws back in. Maybe there's a lot that will happen, and that's what this graph tells you. If you start somewhere, over time, you know your factor of safety is going down. And the more you want to protect yourself against the risk of a failure, the more difficult it is. The best way, if you look at some of these graphs here, when you have a lower factor of safety, is knowing more the variable, taking worst case scenarios. The examples I've given of the four-wheelers is they will design it as suspension, and they put all the load of the unit on one wheel with an amplification factor for hitting the ground, and that's what you get. Now you assume the person does this a certain number of times, and that's more or less the basis for your design. You don't mind as much about the normal driving because it's not what will overload and start cracks in the structure. The counter example of that, this shaft gear is about 7 inches in diameter. It's nickel-based alloy, very expensive. It's for a high-performance boat where essentially the propeller is only halfway in the water when riding. So if I have the shaft here, and then I have the props, say I'm going to just put one in the water. This is the water level, and then you got the other one. It's a very noisy system. But it's only halfway in the water, and therefore you have a lot of bending applied to that shaft. The failure happened at one specific location, right over here. And in terms of what we're going to talk about tomorrow for failure analysis, it has some relevance, because if the shaft is turning, and I have, say, 3 props or 4 props, I would expect that there are 3 or 4 locations that have the same loads. So if I only got 1 crack instead of 4, it means there's probably something going on in that very specific corner. So what happened was a little bit of gouging. When it entered the hull here, so this is the back of the boat, there was damage to the shaft. And even if it was a 7-inch piece, that damage is what initiated a single crack. And the crack grew from that very specific corner here. And you actually see that it's a little darker here. It's essentially a little bit of penetration into the material in the cylindrical portion. And then it grew, and you see these beach marks. This is where the crack was at some point in time, where it was some point later, and then all the way here is where it was before the final fracture. And the guy lost the prop, had to call it towing, wasn't happy. But he learned later that even though this was 6 or 7 inches, very expensive material, he was supposed to replace his shaft every 400 hours. Now, it's what, you know, anything performance cars the same way. You have to rework your engine all the time, because it will eventually form some crack somewhere and grow to the point where now you have a problem. So to some extent, the design for this was essentially the time to start a crack and grow it to the point where it'd be big enough to completely open the fracture. If this was an aircraft, the crack was certainly big enough before he took off to figure it out just by inspection. But these things don't get inspected. So it's, in terms of factor of safety, when I say 1.2, it's if a normal boat's used for, after 500 hours, the guy's going to decide to change it anyway, okay? Because these are high performance. You know, he hit something, he wants to change the whole system anyway, then it doesn't matter. But if it's the same use, when we terms of our probability, if you wait long enough, that's where you have the failure. So putting a value on the factor of safety also depends on what's my probability risk. So if we were normally at 0.1%, and this guy used the boat a lot, now he fell below 1 with this. I wanted to briefly talk about big investigations I was involved with a bridge where nominal factor of safety is 2 to 3. It depends on the detail, and it depends what you're looking at. And that was the bridge in Minneapolis, the I-35 bridge. It happened, I believe, 2007 or 2008. And when you go back after the fact to explain why something that's built with a factor of safety of 2.5 is now in the river on a hot day, okay? This was not a problem with brittle steel or something like that. It was the hottest day of the year, 1st of August. You have a lot of explaining to do. You can start, well, they added some lanes. Okay. It's significant because on a bridge, 70 to 80% of the load on the primary structure is dead load. It's essentially the steel structure, the deck, the whole system is a lot more weight than the cars going through it. I think it's actually intrusive. You know, it's just a lot of concrete on the bridge. So just thinking of that, when we're saying factor of safety of 2 to 3, do we mean with respect to the total load or the live load? It's a big difference. If the live load is only 25% and you say, oh, maybe I have 3 times more traffic, that's easy. It's only 60%. It's still less than the weight of the bridge. But the reality is, on that hot day, they had issues with the bearings of the whole bridge. So when I talked about differential settlement and those concepts, if you're going to have something that long out of steel without expansion joints, the 2 main trusses didn't have any expansion joint. You need to allow for expansion somewhere. So if they had 2 piers in the river or in the embankment, and then you have your cord here, and you keep going, if at one point this is supposed to be moving and it's not moving, what are the consequences of that? Now it doesn't even have to do with the weight of the bridge. It has to do with its stiffness. The stress level that you will develop in some of the joints are just not, they can be counteract in the opposite direction to what you'll expect them to be from that weight and service weight. You're arcing your bridge. You're supposed to be letting it settle. So is that something that was taken into account in the code calculations? No. Did it happen? Yeah, it's just in terms of use and the time, and what I said about the factor of safety going down. Does it mean from now on they're going to take into account the expansion? Well, there are a few things. I've actually taken a class on inspecting bridges after that incident. It had a brand new chapter because they wanted to know more about gusset plates. There was an issue with gusset plates here. And it turns out it wasn't something that they were looking at. But when you think of it, gusset plate is when you go from one big member to a diagonal. You want to have something that's easy to put tubes or different junction in between them to make lap joints. It's very hard to connect 2 big members. So if you go in an airport or in a lot of places, the plates, they are what allows you to connect 2 tubes together, for example. And it's a joints, and if nothing else you learn from this class, joints are more at risk for failure. So they need special attention. And yet, when there were structural engineers that looked at this before the incident, they really didn't pay enough attention to the joints. They looked at the main members. So I hope you can see that factor of safety is taken differently in different industry. The acceptance level depends on the risk you want to take, and there's a lot of experience. Experience is what really matters in terms of how you're going to evaluate the demand and the capacity. So we'll take that over tomorrow. I'm glad everybody seems to be paying attention. Thank you.